Hi, thanks so much for joining me today. Today we're going to talk about Homebrew 68K retrocomputing using low-cost FPGA boards. Now this talk was originally delivered during the Hackers on Planet Earth conference in July 2018 in New York City. Due to some AV troubles, however, the talk was cut short, both sort of on the front end and on the back end, and so the hope is to re-record this talk to make it available in its entirety to everyone and hopefully provide some additional views of the board, close-ups of the board that I've created, and go from there. So let's get started. Okay, so let's talk about who I am. My name's Keith Monahan. I've got a sort of traditional computer science education and background. I manage software teams, including software quality assurance teams. I'm a hobbyist, just like many of you out there. You know, this DIY maker movement is a big thing, and so hopefully this will step it up, right? This talk is going to be a little bit beyond some early projects using the Arduinos and some of these sort of off-the-shelf projects, but I hope you enjoy it. I like solving hard problems. I like challenges. I've always been like this. I'm always trying to do the next generation thing. I will say that comes without it comes with plenty of frustration, right? Because I'm usually attempting these things that are just outside of my reach. I have some background in this. I've been playing with electronics and computers for a really long time. But I like to push myself. I like to get to that sort of next step. And this project has certainly done it for me. So what am I not? So I'm not an EE. I don't even have a minor in it. Little professional experience in electronics, right? So I don't have an official background. So what that means is that you're going to see flaws today in the hardware that I'm going to show you, in the software. Yes, and even with your speaker and your presentation. It's okay. We're all human. I make mistakes, just like everyone, and so there'll be plenty. There'll be plenty of that today. So whenever I talk about building a computer, building a retro computer, one of the first things that might come to mind is sort of assembling components that you bought at Newegg, for instance. You know, go on PC Part Picker, you plug in a couple things, you make a couple posts on Tom's hardware forums. And don't get me wrong, that has its own sort of complexities associated with it, and that's hard to do as well. But this is not that, right? You know, also, if you take a look at sort of some of the Arduino movements with the stacking of the shields, right? We put a video shield and put another audio shield on top of that. That's not really what we're doing here either. And the Raspberry Pis, as neat as they are, I own 2 or 3 of them. They're pretty cool as well, but that's really not what we're doing here. And so, you know, when I talk about building a computer, you know, many projects are assembly projects, right? And so what that means is you go out and you maybe see a YouTube video, or you see some type of website that says, hey, buy this kit, buy these 3 parts, put them together, and then load the software, and then voila, and you've built something. And sure, you can play around with cases and how it fits, and use outdoor enclosures and so forth. But the point is that the software toolchain already exists. You've got some library, you've got some type of support, right? Somebody else has sort of created this thing, and then you're essentially just the users, right? And so as a result, having support for this stuff is out there. Yeah, lots of help because it's a well-traveled path, right? You know, it's like I say on my slide here, it's like eating at a Times Square restaurant. You know, everyone's been there. There's been 1,000 people. It's probably okay. You'll probably have an okay meal. You'll probably pay too much. But it's a little bit different. And what I'm doing here with this project is sort of off that well-traveled path. And it's just, it's a little bit harder, but a little bit more rewarding as well. So, homebrew computer culture. What do I mean when I say that? So, starting sort of in the 1970s, as a result of these cheap available microprocessors that are out there, people started building kit computers. The Altair 8800 is a popular one that you see pictured here. This is at the same time some of the early machines started coming out, like some of the Apple machines. There were certain groups like Stanford and Silicon Valley ties, MIT, of course, some of the big universities where people had education in electronics. Of course, this is sort of naturally comes out. So you buy your CPU, it's relatively cheap. Then you buy some peripheral chips, including your memory, including your RAM, which is pretty expensive back in the day, and I guess still is, depending. But essentially, this homebrew computer culture, right, is about do-it-yourself computing. It's about building something, designing something, sort of not just assembling. And so, just like people struggled to sort of build their own, whether it be on a prototype board or on some type of perf board, right? The same concepts apply. And so I'm sort of bringing this homebrew culture, along with many other people online, to the modern industry. So, like I said, my project's a little different, right? This is a creation project. There's no manuals. And sure, there's manuals for the FPGA, and there's manuals for some of the chips and data sheets and so forth, right? But essentially, there's no YouTube help, right? This is something that I've created and I've built. There's no forums. I can't really go post a message and say that, hey, my computer doesn't boot, my computer doesn't work, right? There could be a million reasons for why that is. And so as a result, it's a little tougher, right? There's also no guarantee of success, right? And so I make some of these decisions, like for instance, how wide is the memory? I use 16-bit wide memory. How wide is the address bus? And some of these are, right, of course, tied to the CPU. And so using the Motorola 68000 CPU, which we'll get into some more detail on, certainly constrains some of those decisions, but there's a lot of ways in which these things are connected together and make a difference in how they work and make a difference in the overall performance of the device. And so this is kind of slow going, right? My argument for a long time has been that the modern computing world takes too much for granted, right? Essentially, that there's so many layers of abstraction that nobody really understands how this stuff works, right? You sort of learn about it in school, you learn about it in college, about some of how the basics work, but then you never really touch them, right? Because you're sort of wrapped around libraries and wrapped around APIs, and once again, you're sort of using other things that others have created, and so I wanted to sort of make my own stuff. The comparison I use on my slide here, right, is like finding a hole-in-the-wall restaurant in Flatbush. And I gave this presentation in New York City, and so a lot of people, I think, knew where Flatbush is. But Flatbush is an area in New York City which is run down. I don't want to call it the ghetto because I think that term's overused, but finding a restaurant there, could be awesome or it could be disastrous, right? And so that's sort of the path I'm taking. So far, for me, I guess it's been somewhere in the middle. So let's not kid anyone. We all stand on the shoulders of giants. So sure, it's a creation project, but my project, just like any project, builds off of the work of others as well. Frederick Requien is the creator of the J68 core. Now this is a soft core, and what that means is that it's a processor that runs on the FPGA, and so I didn't create the CPU myself, right? I also used plenty of books that were written by Clements and Wilcox and Pong P. Chu as I show there. And I do have a list of references at the end of this presentation that I encourage you to look up, because certainly without this J68 core and without work from other people that are a lot smarter than me, it wouldn't have come into existence. Okay, so here's what I've built, right? And hopefully you like the motif of blue painter's tape, right, that holds down the LCD and some of the other components here. Um, I will show you some detailed information. Okay, so if you're taking a look at this board that's here in front of us, top right hand corner is the LCD, and you'll see I've got a little 3D wireframe rotating cube. That's sort of one of the more complicated things I've done on it so forth. It's on the screen there now. If you come around to the right hand side, sort of going clockwise, you'll see there's a battery, right? There's a battery powered switch, along with a physical switch there that I've had since the 1980s. It still works good. It's a big clunking switch, like none of this electronic switch garbage. You'll see there with the bright blue LED, that's the power board, and so that actually converts the 7.2 volts plus or minus that's coming out of the battery and converts it down to 5 volts, and 5 volts powers the majority of the items you see here. Directly to the left of that is an audio board. This takes some output from the FPGA and amplifies it. So I've got some like volume control. It's a 3-watt driver, and that's the speaker you see at the upper left-hand corner. At the bottom is one of the major boards, and this is for video, and so that white cable actually leads up to that LCD. That video board made by Adafruit, everybody should be familiar with those guys, and that generates the necessary LCD backlight voltages that's required. I think it's 25 volts nominally, and then you'll see that the main brains sort of the operation are off to the left there, and so that's the FPGA board you see in green. That large black chip is the FPGA, and then the red board above it is a custom PCB that I created for SRAM memory, and we'll talk a little bit more about that. And then directly above that you'll see this debug LCD screen pictured there. That's where I put some sort of basic debug information. And for what it's worth, right now what I'm doing is trying to find sort of some better ways beyond the duct tape to mount all these boards. And in some cases I've mounting holes to mount these, but I've got to come up with some ways that'll work. There are some wiring that happens underneath the circuit boards. This design, believe it or not, is actually a little bit cleaner than the one I had before. So this is an upgrade, but I'm just constantly trying to improve this. And on my website I call this sort of the Hope badge computer, but as you can see, it's a little bit bigger than a badge. So I've got some work to do to sort of modernize this and so forth. But it's a work in progress, and I'm not in any hurry, as you can tell. So what is it, right? I've spent some time talking about what it isn't, right, and what I'm not doing. So let's talk about what this thing is. So standalone battery-powered computer. It's based on that Motorola 68000 processor. And so remember, this thing came out in 1979. And so, don't expect super smooth animation or, high-speed 3D graphics. And so you've got to sort of, understand that the processor is really old. And so what is that, 30 or 40 years ago? I wasn't a math major. But yeah, it's a pretty old processor. And one of the reasons, I'm using a 68000 for what it's worth is because I'm an Amiga fan, Commodore Amiga. And whenever I was in New York, there were some cheers from the audience there that they were like, "Woo, okay, Amiga is fantastic." So, and so I grew up on those, and I grew up and I spent some time with Motorola 68000 assembler as a kid, sort of as a early sort of preteen. I spent some time working with these chips, so I'm actually happy to be back doing it again a little bit later in life. So the interface, right, is currently console based, right, through a serial port. So I've got a USB to TTL converter that plugs into the board, and then I run PicoCom or Minicom or RealTerm or whatever the case is, basically some dumb terminal serial software to get access to this. So it doesn't run Linux. People have asked me, what OS does it run? It doesn't run any OS you guys have heard of, right? It's essentially my own creation, and I go so far as to say there really isn't an OS yet available for it. Yeah, doesn't run applications from the App Store, right? There were certainly some other 68,000 based computers. The big ones being the Amiga, the Atari ST series of computers, and then sort of later the Macs as well. Some of the early Mac Classic and some of those machines ran those series of processors. And I guess Sun Microsystems, right? They had some of the Sparks, Ultra Sparks, and I don't remember the exact versions. Maybe the Ultra Spark 10 comes to mind. Used a 68,000. And that sort of same generation. But those applications will certainly not run on this board. And so it's a homebrew system, like I mentioned, custom hardware, and it's designed and it's integrated into an FPGA. Now remember, there's a couple different ways you can go about doing this, right? And I've got some slides to talk about the differences coming up. And so this project was completely designed by me. These are all my ideas. I've certainly bounced things off of many people, traded emails with a lot of people, used my coworkers, hi Andrew, to bounce things off of over the years, and they've provided really good, helpful input that's helped me. Most of the sort of the core concepts and so forth were my ideas, and I've tried to work on them through essentially trial and error to come up with a workable design. This project, yeah, is a vehicle for learning, not a particular destination, right? And so I think that if you're watching this video, or if you attended Hackers on Planet Earth in July, that you'll know exactly what it is I'm talking about here, right? Some people have asked me, well, are you going to sell this? Are you going to make money on this? No, that's really not the goal. I'm going to publish everything, open source hardware and software, and let other people build off this, and maybe work on some project that they have particular interest in. But it's really the journey, right? Not the destination. So some skills are required here. So PCB design skills for that custom circuit board. I collaborated with another one of my friends, Brian from Canada. He rocks, really smart guy. He was a circuit board designer in the 1980s, and so I'm certainly borrowing some of his skills to help me bring it to light. Got to know 68,000 assembler, right? There's no C, there's no sort of advanced tool chain yet for this thing, and so you've got to work with assembly. I will say that working with assembly has been refreshing. It's really nice to get down and dirty with the hardware. It is hard, once again, when you don't have libraries, when you don't have fonts, when you don't have literally anything to build on. It's nice, but of course it's hard, which is okay. Electronic circuit design, including building and interfacing with memory controllers. And so, memory controllers seem like a popular sort of undergraduate, final sort of a project towards some of the advanced classes. And I'll say working with them can be a real pain in the butt. It really depends on the type of memory. Like, for instance, memory like DRAM that requires refreshes, which requires a 12-step initialization process in order to work, can be a challenge. FPGA skills. So FPGAs are a thing of themselves, right? And so in addition to sort of the knowledge for the various, the CPU, the hardware pieces and so forth, FPGA designs have their own sort of set of required skills. So in order to describe our hardware inside the FPGA, we use a language called Verilog. Verilog's a popular one. Another one is called VHDL. Verilog sort of more closely resembles C, although it's not really procedural like that. And so we'll talk about some of those differences soon. And so computer architecture and organization, where does your ROM live? Where does your RAM live? can you be displaying data on the video screen at the same time you're performing another operation? Are there chips that are independent that run? Do you support DMA? Right? There's a lot of different design decisions that have to be made. Some of them, even though they'd improve performance, are so complicated, and you've got to decide like how much time do you want to spend on on each individual part, because all of everything I've created so far can be optimized. It's not perfect, right? And so it can always be refactored and rewritten to be better and faster and so forth. So all those sort of decisions come into play. So yeah, I made the decision to go integrated versus discrete. And so let me explain sort of what the difference is there. Right? Whenever I talk about integration, what I'm talking about is bringing all of these individual Verilog components, including the J68 core, right? That's the soft core CPU that runs on the FPGA. All those things, and sort of dropping them on the individual chip, right? One of the methods you could use here, right, is to use separate chips, right? And so what that means is you get your CPU, and you get your RAM, and you get your ROM, and you plunk all these separate chips on the board, like you see in the picture here, but you can see how messy this gets, right? Yeah, address buses 23 bits wide, the data buses are 16 bits wide, so all of a sudden this is a lot of wires going around the board. And because the 68000 CPU is a memory mapped device, what that means is that anytime you're attaching peripherals, those peripherals are going to be connected somehow to the address bus or the data bus or some chip that's going to function like an arbiter, like for instance Agnes in the Commodore Amiga. Yeah, so you either end up with a large custom PCB or wiring that looks like that. Now an alternative way here is to sort of choose FPGAs, and that's what I've done. Here is yet sort of a third way. Here's that sort of custom PCB. And of course what that custom PCB lets you do, right, is have all those wires, but just be a heck of a lot neater. Now there's a lot of skills here. This is the Kiwi 68K computer. This thing is awesome. This has been years in creation. This is definitely the real deal in retro computing done right. You can imagine how much time and energy went into, for instance, just laying this board out, right? Getting the circuit board ready. Could be a big deal. Okay, so specs. So the specs for this particular retro computing that I'm building: 68K software CPU, like I told you about. It's slower than a real 68K, but it's clocked faster. So what do I mean here, right? So a regular 68K runs somewhere in the neighborhood of 8 megahertz, 10 megahertz, 12 megahertz. And of course, some of the later generation ones, like the 68030, run a lot faster. But this particular design of the soft core requires a lot more cycles per instruction, and so as a result, even though it's clocking faster, and I'm running this right around 66, 67 megahertz, because of those extra cycles, wouldn't be as fast as a 68,000 that's actually clocked at 66 megahertz, right? And so, on one hand it's slower, but then I clock it faster sort of to get some kind of decent performance out of it. And I am getting reasonable performance. So I get 4 MIPS for sort of general instructions. So like, for instance, adds and subtracts and I guess maybe not really moves, but some of your simple instructions, I'm getting about 4 million instructions per second, which I think is pretty good. And I get 1 million instructions per second for multiplies. Multiplies are complex instruction on the 68000, as are divisions. And so those are really CPU intensive, and so you've got to be careful using them. Some of this 3D work that I've been working on currently needs a lot of multiplies, and so it's really hard to have sort of fast 3D performance whenever those are such expensive operations that are required for some of that sort of matrix math. So I've got multiple types of memory that I on this board. So I've got the SD RAM that's on the board right now using an Altera memory controller, which then has been glued into the CPU with my code. We've got user flash memory, which is actually on die with the FPGA. That's where I store my ROM, right? And so this thing can boot up and boot directly into my code. That red circuit board that you saw, and I think I've got a close-up shot of this coming up. That red circuit board currently houses just one 4 megabyte 10 nanosecond SRAM chip, and that's what I use for my frame buffer. And I'll talk about sort of why I do that in a little bit here. One thing to note about SRAM, and one of the reasons why I went through the trouble of creating this add-on board, is that the interface is very easy to use. You put the address, you put the address on the port, you enable the chip, and then you wait a certain period of time, and then you can read from the chip. All the reads and writes are very deterministic, and it's always 10 nanoseconds. And so what that means is from the time you sort of assert this stuff till the time you have either your read data or your write data has been actually written on the board is 10 nanoseconds. And this is really useful, like I said, for a frame buffer because you know, whenever you're driving a video display, you have to keep that data flowing. There really is no pausing without causing some kind of negative video effect. Okay, what else? Multiple real-world interfaces. So it's got a 7-inch touchscreen on it. I'm currently running it at 800 by 480 by 12 bits. The display itself supports 24 bits, but I need to build some further things out in order to take advantage of that full 24-bit color on the display. I also support VGA, so this is a VGA interface, you know, 15-pin, is it a DB15 connector. Serial UART for the console port, we talked about that a little earlier. An integrated DAC, and so that means inside the FPGA we have some logic that functions like a DAC. And then, and this was on the board as well, an external DAC using a Cirrus Logic 4335 chip. Also, for a little bit higher quality audio, is sort of in the works. And then also that debug LCD. That was that blue LCD that you saw earlier. Yep, and here's that sort of close-up picture of what I wanted to show you of the FPGA board and then the custom SRAM circuit board. So you see that main eval board, it's relatively small, and I guess I need a banana or a quarter or something for scale, but the board's relatively small. And you know, one of the points of this talk is that this particular FPGA board was $30, and so you know when you buy FPGA evaluation boards, those can be very expensive. You know, those boards can get up into the couple $100s, and I have a couple of those boards. But you know, I wanted to see what can I do with sort of you know, limited resources, right? So just like sort of the computer designers of yesteryear, who only had a really limited RAM and limited CPU power and so forth, I wanted to use those same concepts and not go overkill, because in a lot of ways, if you go overkill, it's a little bit easier to do this, and I wanted to challenge, like I said. On the left-hand side, you'll see the circuit board that I designed with help from my friend Brian in Canada. That's an SRAM chip that you see listed there, that you see shown there in the top left-hand corner. And that's, I use ISSI as the brand name for the SRAM chips. Great chips. You know, an interesting point to note is that SRAM chip was about $24, and so kind of expensive for a memory chip when you consider that sort of that whole right-hand board is only $30. And really, I think even that little, even the FPGA board connector, I think those connectors bought in low quantities are fairly expensive. I think those connectors might be like $10 a piece or $8 a piece or something like that. So kind of expensive, but really simplifies dealing with memory, and so really money well spent instead of spending more time and effort writing memory controllers. So DRAM has bandwidth, but I need consistent latency. And so this is sort of what I was referring to earlier, right? Video is unrelenting in its thirst for data. And so what that means, right, is that you have to constantly have that data available immediately for the display. The display is not going to stop. It can't stop and sort of wait for that data to show up, right? Most displays, and this is becoming a little bit less true, but with modern LCDs, but most displays don't have any memory, right? So they can't hold the contents of the screen at all, and so you've got to constantly feed this, right? And so what do I say here? The maximum acceptable latency is defined by the pixel clock, which is a function of the horizontal refresh and resolution. And so essentially what I mean here, right, is that, you know, your horizontal refresh rate basically describes how long it takes to draw a particular line. And so you take that time, and let's say that time is, I don't know, 15 milliseconds, and what you do is you take the resolution and you divide that into that frequency, and then that tells you sort of how much time you have for each individual pixel. And so what this does, right, is what does it do? So what this does is defines this very narrow window for you to actually put the video data onto the particular data lines for the LCD. And so that's important, but like I said, it's very unrelenting. And so with SDRAM, you have variable latencies, right? And so what this means is that depending on where inside that memory range you're trying to access, it changes how long it takes for a read to happen. And so, for instance, if you've got a page open and you've got a particular row open, that you can access data within that particular area very quickly, or at least very consistently from read to read. But then if you go to a different page or you go to a different row that has to be opened, closed, and reopened for the next one, then that next pixel's data is going to take a little bit longer. The next video data will take a little bit longer, and so that's makes it tough. Now there are ways that you can buffer and read ahead and sort of keep this by using, for instance, a FIFO or something where you could ask for data in advance of actually needing it, and so you could have, for instance, a particular line buffer. But anyways, using SRAM is a lot easier and simpler, and getting that 10 nanosecond access, which is always 10 nanoseconds no matter which part of the memory you're trying to access, is really a huge win, and that's why I created that board. And so here's sort of what I was talking about earlier. Here's VGA timing, right? And this is stolen unabashedly from Wikipedia, which I've cited as my source there. And so you see that big region there, that active video region, right, which is the section in blue there. You know, that's when the video data is actually transmitted. And so in this particular example, and this is the example for 640, and I think this is this is the horizontal timing, right? So 640 pixels have to be transmitted in that 25.422 microseconds, right? And so if you divide that out, that tells you, you know, how fast you have to transmit a pixel. And you'll see the pixel clock frequency, and of course all these numbers are sort of essentially related. You'll see the pixel clock frequency is around 25 megahertz, and so what that means is that you've got to get a pixel on there, you know, with whatever 25 megahertz, whatever period of time that corresponds to, right, which is 1 over that frequency. Whatever that period corresponds to, you've got to be able to get that data in there consistently in order so you don't have essentially negative effects in your video in terms of the like the screen tearing or the video not lining up and so forth. So okay, so when I talk about Verilog described hardware, right, all of the hardware lives inside that FPGA, right? And this is a new concept, I think, for a lot of people. But essentially what you do is you describe that hardware. So that means you describe the CPU, you describe a video driver, you describe a UART. And so these are some of the hardware components that are currently in place. And so I've got that modified version of that that J68 softcore CPU that we've talked about a couple times. I've got a 6850 UART. So the 6850 was another Motorola chip that was designed for interfacing with a serial port. The one I'm using comes from an Atari project, an Atari ST project, which was like a really good match for the softcore for the J68. I'm using a softcore YM2612 for music, and so this chip, as you might know, is inside the Sega Genesis and inside a few other devices like maybe keyboards and so forth. And I chose this chip for a couple different reasons. It is used in sort of some 68K computers for music, and so that was part of the interest that I had in it, but also it sounds sort of retro. Yeah, so the YM2612 softcore adds some really nice retro music components. A debug LCD driver, remember that blue LCD that you saw, that smaller one on the left hand side of the board. I wrote the driver to drive that. I got that off of eBay relatively cheaply. Lots of memory controllers. This is complicated things, right? That flash memory, even the SRAM, right? You've got to have some interface that sort of talks to the SRAM and asserts the appropriate signals at the right time in order to make that chip do the things we want it to do. A Sega Jim music parser is something that is at least in beta right now, and I can sort of play a single piano note by using this Jim, which is essentially a Sega Genesis music file format, and it can sort of parse this particular file to be able to produce music. I'm almost at the point where I can play songs. I'm close to that, and so hopefully you'll see that soon enough. Other Verilog described hardware includes a video driver for the frame buffer that supports both VGA and ELCD. Font generation and overlay. Remember that you get nothing for free, and so I've got to be able to define what a font looks like. The font generation that I've taken comes from a book that I cite for the most part from an author called Pong P. Chu, that FPGA prototyping by examples. And so I've used some code out of there in order to generate fonts. And then lots of glue logic. So what's glue logic, right? So just because you have all of these different parts written in Verilog doesn't mean that they'll necessarily talk to each other. And so you've got to write glue logic, and this glue logic is what connects together all these different parts and allows them to talk. This is sometimes a harder thing, right? Because remember that I'm taking bits and pieces, in some cases that I've written, in some cases that came from the book, like I mentioned. Sometimes they're written by somebody else who wrote this J68. If you got to connect all this together, they're not always directly designed to talk to each other, and so it requires some work to make that happen. Okay, so FPGAs. What are FPGAs? So they contain these programmable logic blocks, and you write in languages like Verilog and VHDL that I mentioned earlier to describe how those blocks should be configured. FPGA vendors, their IDE, their development environments, you compile and synthesize this code that you've written in this hardware description language, gets compiled down into a bit stream, and then that bit stream gets uploaded into the FPGAs, and that's basically to configure essentially the logic fabric to describe that particular hardware, to implement that particular hardware. And so your code you write it in modules. These modules have inputs and outputs. They commonly contain clocked processes, right? And so what does that mean? So essentially, right, you've got these various modules, and these modules all have to coordinate their activities. They got to coordinate functions. And so we use a clock, right, that essentially tells all these processes to act, for instance, on the falling edge or act on the rising edge of this particular clock, so that all of their functions are coordinated and synchronized. And so, yeah, these modules, where certain conditions are evaluated periodically to decide to take action or not. So what does that mean? We have a particular logic signal that falls, and then maybe we have to respond to that. Maybe we have to raise some other signals. Maybe we have to put data on the bus for the memory chip to write it into memory. Maybe we put sound data onto the connection to the DAC, which then causes music to be generated, right? Big vendors include Xilinx, Altera, Lattice is another one that I've heard more and more recently. Altera was just recently bought by Intel, and so we're likely to see some big things coming from them soon as well. So HDLs can be miles away from other languages. So a lot of normal languages, when we talk about languages like C and C++, and Java, for instance, are procedural. What does that mean? That we have sort of top-down execution? But in this particular case, HDLs don't work like that. You can have sort of a whole block of code that gets executed in parallel, all at exactly the same time, not one after the other, right? And so I say here, like, no fetch, decode, execute cycle, right? So FPGAs are not CPUs. They don't work like CPUs. Now you can take, just like I've done, the J68, and then things that happen within sort of the context of the J68 are procedural, and then you have sort of part of your hardware acting in a procedural manner, but the FPGAs themselves don't work like that. FPGAs are blank by default. They don't do anything out of the box. So you get an FPGA, out of the box, you plug it in to your PC via USB, and it doesn't do anything. It doesn't implement any logic function by itself. And so like I spoke a little bit about earlier, you describe multiple modules and you connect them together into some type of system. And so in my case, what is it? A CPU, a video driver, a sound driver, an LCD driver, right? And all these things sort of come together to form a system. And so I'm sure some of you have heard this term, system on chip, and this is essentially what I'm building. Some modules might only talk between themselves, and so that means that we've got 2 or 3 modules that are on the chip itself. They talk to each other, and then some of them will talk through I/O ports, right? And so that's when we're talking about leaving the FPGA and then connecting to an LCD, connecting to a serial port, and so on. And so, systems can contain something very simple like a single NOT gate, or they can contain full CPUs, video cards, routers. And so really the complexity that an FPGA can support really comes down to the number of logic gates it supports. Now, this $30 FPGA board that we're using here only supports something on the order of about 8,000 gates or so. Is that right? 8,000 logic elements, which would translate to more than just 8,000 gates. But the point is that one of the criteria when you're selecting an FPGA is to have some particular logic capacity associated with it. Now, of course, the vendors don't agree on how to do this, and so they use different metrics to sort of describe even the unit of measure of sort of how much logic will fit on a chip. And because they have this very complex synthesizing software, there are ways that some logic functions can be, for instance, synthesized into less amount of logic space in Xilinx than in Altera. And this is a whole completely separate talk that could happen, but it would be somebody other than me because it's pretty complicated and I don't claim to fully understand it. And so here's a screenshot here of Altera's Cordis. What you see here is essentially a whole bunch of files with .v extensions for Verilog on the left-hand side. And then you've got sort of the different phases of the compilation process on the left-hand side. Right in the middle of the screen, you have the actual code itself. Here's an example of Verilog, and looking at this Verilog here, this is something that I've wrote and doesn't correspond to anything interesting enough to describe right now. But then you have sort of your what's happening at this time, and I could tell by all the green check marks on the left-hand side that this was right after I'd gotten finished programming something. But long story short is it's an IDE, and if you've used Visual Studio or Eclipse or NetBeans or any of the other myriad ones, including the new Vogue ones, this is pretty similar and shouldn't look too foreign to you. And so let's look at a particular module now in Verilog. And so this is just the module header that you're looking at. And essentially what the module header describes, and this is not too dissimilar to other languages like C and Java and so forth, where you essentially have your inputs and your outputs. Now we don't really call them arguments, but you could probably look at them the same way, right? We've got some things that are signals that are coming into the chip and some things that are going out, right? Now this is the top module, and so what that means is that it's usually interfacing with the real world, and so these are signals that are leaving the FPGA, going out of the chip itself, going and connecting to something else. And so let's take a look at this real quick. So one of the things you see is key, that very first line where you see input 3:0 key, and so that's a bus, right? And that actually represents 4 keys, and so this is 0 based, right? So 3, 2, 1, and 0 are all different switches, and they could be up or down. And so you'll see that that's a particular bus of switches. You'll see that input clock 50, B5B. This is a 50 megahertz clock signal that comes into the chip. Now remember, I said that this project runs at 66 megahertz, and so we run that 50 megahertz into what's called a PLL, a phase lock loop, which is essentially like a clock generator that takes in 50 megahertz, but then spits out a bunch of other frequencies that are necessary to be able to run the device. And you'll see that, for instance, the SD-RAM, lots of connections out to the SD-RAM. Remember I told you before it was complicated? I wasn't kidding. And so there are a lot of other signals that all have to be asserted and set up in exactly the right manner in order for them to work properly. Okay, so when we talk about finite state machines, when we talk about building hardware within Verilog, a common construct is called an FSM. I think whenever I was in New York, I took a show of hands who recognized sort of this FSM description, and I got some hands. There is a concept of a software-based finite state machine, and if you've ever implemented something like TCP or any myriad of other protocols where you have different states involved, where you move between those states based on certain actions, then this shouldn't be a completely foreign concept to you. Unlike a CPU, where the processor is always advancing this program counter, right, where it's fetching its next instruction, FPGAs need hardware to allow for a sequential execution of action. Okay, so what does that mean? Let's unpack that a little bit, right? So remember, HDLs aren't procedural, right? And so that means that if you want to do something and then do something else and then do this third thing, that even the moving between those different states, moving between those different lines or those different actions, have to be controlled by something, and that something is the FSM. They start in some initial state, and then after something occurs, and so what does that mean? Somebody pushes a switch, a signal falls, a byte of data is received on the serial port, right? Then it moves to the next state, which would take the corresponding action associated with that particular input, right? I give another example here in the slides. This could be a counter or a timer reaching a certain value. Could be an external button pressed, okay, and so on, right? And so the point is that there's some type of signal that comes in that causes the finite state machine to react and do something differently than it had been doing in the previous state. And so this is a little diagram I drew just a couple minutes before the presentation that I gave a month ago. But essentially, we've got three different states here, right? And so we start sort of in state 1 here in the upper left-hand corner where it's idle. And it's going to stay in that idle until something happens. That something happens in this particular case is sort of like a trigger event. That trigger caused the FSM to go into state 2. And once we're in state 2, now we're going to do something. So based on that action, based on that trigger event occurring, we're going to go into state 2 and we're going to do X and Y, which is different. Remember, we weren't doing X and Y in the initial state. And then something happens. Now, this particular something happening isn't necessarily a trigger event. It just happens to be the next clock tick, right? And so that means that the trigger sort of kicked things off. We went off, we did X and Y in state 2, and then the very next clock tick, we went to state 3, we did Z, whatever that means, and then we're going to wait for a push button that's going to take us back to state 1. And so essentially this is the way this works, right? We're going to continue to do some activities based on sort of a trigger occurring on the clock ticking or on pushing a button. Okay, and so if we talk about 68K CPU, it's a memory map device. Now I know I mentioned that earlier, but let's unpack that a little bit too. So there are no GPIOs, right? And so if you've messed with a Raspberry Pi, if you've messed with any type of microcontroller, there's usually some spare general purpose input-output ports, right? These are spare connections that then you can hook up to external hardware. Well, if we take a look at the pinouts here for the 68000, here's what you'll see. You'll see a bunch of address lines. You'll see a bunch of data lines. But what you really don't see here is any GPIOs, no spare unused pins. And you got to remember, right, that this chip is a 64-pin chip. And as you may know, that the cost of producing a chip is related to the number of pins, and 64 pins, especially in a DIP package, which is what this was available in, is pretty expensive, right? You really don't see DIP chips getting much larger than this. Usually, once they go beyond 64, you might see them in a PLCC package, for instance, or some other type of package, because this just gets very expensive, and the physical chip gets really large. And when the physical chip gets large, a lot of times this implies that the circuit board that it plugs into is large as well, and then your costs are also related to the size of that circuit board. And so getting back to this memory map device, so this means that the hardware must be connected to the memory bus. And so that's any type of device you can imagine, from a video driver, sound driver, any hardware that you want to connect has to go through that memory bus. All that hardware access is done via reading and writing in certain address ranges. And so what this means is that there isn't any signals, for instance, that say raise pin 15 or raise pin 27. If you're used to seeing that on some of those other devices that I mentioned, that's not what happens. And here, you simply move a particular value, a particular 16-bit value, to a particular address, and then your hardware that is sitting on that memory bus, your custom hardware, has to sit there and wait and say, oh, hey, I'm going to be activated whenever I see data arriving on the bus. Now there are address decoders, and I'm going to show you mine here in a minute, that can sort of help, provide a trigger for an external chip or an external module to work. And I'll show you sort of how that works. The only exception on the 68K for connecting external hardware is the 6800 bus. And I talked with somebody at the conference about this in detail, but essentially, do you see those pins that are all in a row, 19, 20, and 21? So VMA, the E clock, and then VPA is essentially 3 pins that are used for older 6800 peripherals. Now remember, this isn't a typo. I don't mean 68,000 here, I mean 6800. There were some older 6800 chips that could be connected via just those particular pins, but that's really the exception for connecting external chips to a 68,000. My memory map, and so here's the address decoder, and this is something that I rewrote. And there's a couple different reasons why I'm showing you this. A, I'm sort of showing you how I've constructed my address decoder, but then it also shows you the memory map. And remember what a memory map is, right? This is essentially saying which hardware lives where, right? Because being a memory mapped processor, certain memory regions belong to certain hardware devices, and this is sort of the breakdown. And so what are some of the things you see here, right? You see the SRAM lives at 820,000 hex, right, and up. You'll see the SDRAM lives at 20,000 and so forth. And so remember I talked about computer architecture and some of those design decisions having some effects? This is essentially me selecting different memory ranges. Now, you know, there might be some sort of competitive advantage to having your hardware located at certain addresses versus other addresses, right? And so you'll see that I implemented a 32-bit counter, which is available in sort of right around hex address 10,000, right? 10,002, 10,004, you'll see, so forth. You'll see that I have a certain amount of ROM that sits there, a certain amount of RAM that sits there, and then you'll see some other things. You'll even see a comment that says this doesn't appear to work, and you know, I don't think I've dug in deep enough to figure out why that doesn't work yet, but you'll also see that I have a default data value that gets put onto the data bus, because you see that RD underscore data is actually a 16-bit bus that that in the event that we don't drive it with something, I wanted reads that happen outside of these ranges to return a value, and I picked B00B for obvious reasons here. So this way, whenever you read, if your software comes back with that particular value, that you can say, wait a minute, what's happened here? You know, I must have been reading a invalid memory address range, because remember, there's something like 24 bits of address space here, and so and I'm not obviously using all of that space. Software. So I started off by using this ROM monitor called VUBug that was written in 1988 by a student at Cornell University. It targets that 6850 chip, which, if you remember, that's the serial UART chip that came from the Atari project. Because that software targets the 6850, the modifications that needed to be done to VUBug to actually support this hardware was fairly limited. And so I think it's pretty cool, right? So you can essentially imagine us taking this soft-core CPU that was sort of rewritten semi-recently, right, within the last, I don't know, 5 or 10 years, and then you take software that was written in 1988, you take this other UART that was written at some other point, and all this stuff just happily plays together. It's really beautiful. It's really cool, I think, that we can do this, that this even works even on a fundamental level. You know, I've talked to a lot of people. You know, one thing about hardware is that if you power this thing on and it doesn't work, a lot of times what happens is absolutely nothing, right? And this is hard, right? Because think about when you write some software in Java, for instance, and you compile this and you run it. If it fails in some way, you usually get an error code, right? You get some type of error message. You get some type of, sometimes it won't even compile properly, right? But in this particular case, in hardware, if the hardware doesn't boot, if you don't see anything on your screen, it's tough. Now, there are ways you can get in there and debug it, obviously, but it's really kind of tough because when hardware works, it can fail in sort of very major and mysterious ways. So the 68K assembly that I'm using uses the VAS MM68K assembler, which really is surprising how well it works. I'm able to give it 68K assembly written in a variety of different formats, if you will, because remember, right, in addition to writing the 68K assembler myself, I'm also taking snippets of 68K assembly from other places, and really this assembler just sort of handles it. It's really fantastic, and I've been very happy with it. Code is first assembled into machine language, right, converted into a MIF file, which is then programmed into the UFM. That UFM is that flash memory. And so that's sort of the process that this works. Currently using a monolithic piece of assembly that includes some library functions like pixel, line, circle drawing. And so monolithic piece of assembly, yeah, this is ugly, and this is one of the reasons why I've been a little bit reticent to release my code, because it's a little ugly, right? Essentially, you've got this one big fat assembly language file, and that contains all of the sort of software functions. So that has to be broken down and modularized a little bit, and just applied some, modern or really proper programming principles. That just has to be done, and I haven't done it yet, and so that's something that's on my to-do list. Yeah, so remember that for this particular board, right, there is no C toolchain. There are no other languages. Nothing else is supported. Now, I have been able to do, using Easy68K, I have been able to take some C files, limited procedural local functions only, C code, compile to assembly, and then sort of bring that assembly down into my platform, but it's really just not ready yet. Okay, I wanted to give you an idea here as far as text generation goes, actual hardware. So this lives around hex address 5000, right? And what you do is you write the lower 7 bits of the 16-bit word, and so where you see those Y's there and that slide there, you put the 7-bit ASCII value in there, and then it'll show up at the particular location that matches the address that you've given on the actual write, right? And so essentially, if you imagine a grid of 100 by 30 characters, with the upper left being 5000, and then the other locations there, and so that means upper left character would be 5000. The next one over would be 5002, 5004, and so forth, coming over from the top left-hand side. And so what you'll see here is essentially my depiction of that. And so you'll see sort of this, sort of layout here that is a grid of 100 by 30 characters, and explains to you exactly how you use this. You'll see that I specify sort of the odd byte values here, but that's just because we're using the lower 7 bits. All of your reads and writes would still happen on even addresses, because the 68,000 does not use the last address bit. So essentially, if you look at 5000 or 5002 or 5004, even though the data lives sort of 1 byte beyond that. And so that's sort of an example, right, of the text generation API and what that looks like. And remember that there are a lot of people that are used to using an API, but sort of only one side of it, right? In this particular case, you essentially have to define what the what the hardware looks like and how the hardware is going to react to the software, and then write the assembly language commands that actually put the text on the screen. So what can this thing do? So your main access is through your serial console port, right? And so you can't telnet into this thing. You can't use a web browser to access it or anything like this. And so right now, you come in through the serial port. We can print text on the screen like we talked about. You can do simple graphics like lines and circles. You can debug your software through the debug LCD that I showed you. You can use graphics that use the frame buffer. And so what that means is you put certain color pixels, certain color data into certain memory locations, and those memory locations will then be drawn on the screen, right? And so you can put a series of red pixels in the middle of the screen by putting them sort of in the middle of a memory area, essentially. Rotating 3D wireframes, and old school Sega music, which, like I said, so close to, I could do sort of a single piano note here, but it's going to add on. I'm going to attach in this presentation some live video that is the actual device as it works, rotating that cube, show you the debug LCD, and maybe play a tone so you can get an idea of what this is going to look like. I wouldn't say at this point that it's impressive. I think that if you peel back all of the layers to understand what needs to be done, I think it's impressive. But I think we're still I still have to put together some fundamentals to really be able to turn this up, to get it so that it's a little bit more similar to the capabilities that you're used to seeing from computers of that same generation, like the Amiga and the ST. So I've got some work ahead of me to really to turn it up. But everything builds on the work I've done previously, so I'm getting there. And so, yeah, my reinventing the wheel has its struggled, and so a lot of things like font generation and frame buffers and line and circle drawing algorithms, like these things are very simple, and I'm very much reinventing the wheel. There's a famous JFK moon speech, and JFK said, "We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they're easy, but because they're hard." And so that's the end of my presentation. For future expansion, I would like to do keyboard, mouse, SD cards, even wireless networking using a fairly popular chip called the ESP8266. I need to refactor that code base. I talked sort of earlier about the state of that code base. It needs to be improved. I need sort of a better IDE. Right now I'm not happy with how that's working, so I'm checking in some other editors that I can use with Verilog plugins to still get sort of some color coding and sort of some basic functions there. I need to build out that C environment. If I could compile C programs, I think things would sort of take off for this. And then, port some flavor of BASIC, right? All these computers from sort of the 1980s and the 1990s had some flavor of Microsoft BASIC or QBasic or whatever they are. I think that if I had something like that, then I could start to write little bit higher level applications that might work a little bit, be a little bit easier to create things that are a little bit more impressive. And so here's my resource list that I sort of spoke about. A number of different books, mostly Alan Clements and Alan Wilcox. Those books are fantastic. Anything you find from them are good. Pong P. Chu, I mentioned that FPGA prototyping book. The Art of Electronics, which a lot of people abbreviate online as AOE. by Horowitz and Hill is sort of very famous and super useful. There's some other sites like FPGA for Fun that I mentioned. And then even Marky Gesture 68,000 tutorial has helped me greatly in terms of writing some 68,000 assembly. My blog at techtravels.org, it has been in operation for a long time, maybe 12 or 14 years, excuse me. Variety of different projects on there, including real-time video scaling, a floppy project, a DIY PCB inspection camera that uses a Logitech C920, sort of the guts of that inserted into a Lithuania milled aluminum case that accepts different types of lenses. This is a pretty neat project I worked on. There's also a PDP-10 re-implementation on FPGA that I'm hosting on my site for somebody else who has similar interests to mine. Thanks so much for your interest. The plan is to make this stuff all open source. I'm going to put everything online, including this presentation, as well as the source code and the hardware and so forth. If you have any questions, feel free to reach out to me. It's Keith, Keith, at techtravels.org. Thank you very much.